Hello. Today, we'll be looking at apparent, active, to an extent reactive powers, and power factor. Apparent, active, and reactive powers, and power factor. Now, all electrical equipment, regardless of their size, requires a certain amount of electrical power to operate. This power is designated in watts, or sometimes indicated by the voltage and current requirement, from which we can then determine the wattage of the equipment. The power information can sometimes be ascertained or found on the nameplate. So for some appliances, you'll see here we have 220, 240 volts, and we also have the current that the appliance will use, which is 0.55 amperes. In other instances here, we are shown the 180 watts. So there's nothing to calculate. We can see the power consumption. And here we have, again, the supply voltage and the current that it utilizes. So we can determine the actual power of this equipment. There are, however, equipment that in order to properly operate require power known as reactive power. And reactive power is dependent on the presence of inductance or capacitance as part of its operations. And for inductive circuits or inductive equipment, these would utilize things like motors. Large motors would consume inductive reactive power. Now, the actual or true power, as it is sometimes called, required for operation, and we mentioned this before, is measured in watts, and it is designated as P. So the actual or true power, designated as P, is measured in watts, while the reactive power is measured in VARs, which means reactive volt amperes, and is designated by Q. So we have P for active or true, and for the reactive, we have Q. Now, the mathematical relationship between the active and the reactive powers can be shown using vectors. So for the active power, that will be on our horizontal, and for our reactive power, that is on our vertical. So we have P on the horizontal, and we have Q on the vertical. And of course, they are at right angles to each other, right? So we see a right angle there. Now, when we combine those two powers, so the combined power required to supply both the active and reactive powers is known as the apparent power. And this is designated using S, and it is measured in volt ampere. So it's really a direct product of voltage and current. Now, as I said, the relationship between the two is shown as us closing the triangle. Yes? So we have here the apparent power S, now being the hypotenuse of the triangle, which was the other two sides created by your active power P and your reactive power Q. Now, for residential customers, owing to the type of equipment used, the amount of reactive power required is quite negligible when compared to the actual power required. So the reactive power is almost zero. The apparent power is therefore equal to the active power that is required, because there's no need, there's no large reactive component, then P is equal to S. And we show that in our diagram here. So Q, in this instance, will be equal to 0. And that's for residential customers. Yes? As the active power demand increases, so too does the apparent power. So for a fixed active power, meaning the equipment has not changed in terms of the power demand, the true active power demand. If the reactive power demand increases, then we are going to see increases in the apparent power. So if here, I'm going to show increases in my Q. So for a small Q, I get a certain value of S. As Q increases, it means that the length of my hypotenuse is increasing. All right? And so the larger Q is, so as Q increases, for a given P, as Q increases, S also increases. The increased magnitude of the apparent power, therefore, results in an increase in the angle between the apparent power and the actual power. So if we go back to what we have there, here, with the smaller s, that would be my angle. As s increases, the angle increases in terms of magnitude. Okay, so the more apparent power that I need to produce for the same active power, remember, this is the active or true power, that is what is being demanded. That has not changed, but as Q changes, S changes. And we are saying that these angles, yes, the angle between S and P will increase as Q increases. And that angle is known as the phase angle, and we denote it using phi. Right? Now, in combination with the reactive power, the apparent and active power, as we have shown, forms a right angle triangle, which results in a trig relationship or trigonometric relationship. That is, P is equal to S times the cosine of phi. And cosine phi has a special name. So there's my angle, there's my phi. It's the angle between S and P. And the name given to the cosine of the angle is the power factor. So the power factor is given by cos phi. Now, what we know about the cosine of an angle is that as the angle increases in magnitude, the cosine of the angle, so as phi increases, the cosine of phi gets smaller. Okay? It means, therefore, that the smaller the angle between S and P, smaller the angle, it means that it will have a higher cos phi, or in other words, a higher power factor. So let us try and understand the implications of that. What we are saying, therefore, is that where for smaller values of S to supply given value of P, to supply P, we operate with higher power factor. All right, so circuits with high power factors requires smaller S values for the same P. Now, given that the cosine, as we said earlier, is inverse proportional, so a higher power factor means less apparent power is required to supply a given load. That's what we were explaining just now. So for a residential customer, what we see here is a small phase angle because the reactive power demand is small, or we can actually say almost zero. Okay? For industrial customers, however, large customers, we find that the angle between S and P is larger, so they operate at a lower power factor. Now, why is all this important? Why is power factor important? The thing is that especially for industrial and commercial customers, the utility company uses the apparent power to calculate bills. So they are not looking at P, they are looking at S. So for the commercial customer, it is in his interest that he operates with a higher power factor. And for that, or to achieve that, we operate or we seek to implement what is known as power factor correction. And power factor correction involves seeking to make the power factor higher. Or in other words, find ways of reducing the amount of reactive power demand, thereby lessening the demand on S. So in summary, active power P is the power required for operating the equipment. The apparent power is the product of the actual current and voltage supplied to the circuit. And that's key. It's a power supplied to the circuit. Not necessarily the power consumed by the circuit, but the power supplied to the circuit. And the power factor is the cosine of the phase angle, which is the angle between the apparent power and the active power. I thank you very much for your attention, and you can look at our upcoming videos which provide you with examples, worked examples, and opportunities for self-test. Thank you.